Hello, good day everyone. Again, this is Gabriel Gamana. In this video, we will tackle the first topic of open methods under Chapter 1, the so-called fixed point method. But before I dive into the topic, let me first discuss the open methods. So let's start. Open methods are methods or process that requires only a single starting value of x or two starting values that does not require to bracket the root. It means that if I have an equation x squared plus 8x plus 15 equals 0 with a root of x equals negative 3 and x equals negative 5, the solution will possibly converge with the initial limits of x equals negative 2 and positive 1. But unlike the bracketing methods, who always converge with the proper limits, the open methods are prone to divergence, or in other words, the solution will not satisfy the requirements. So we can now dive in to discuss the fixed point method. Fixed point method or one-point method or successive substitution is a method that rearranges the function to produce another equation that will be used for the iteration. Say for example, f of x is equal to 0, where the function is equals to x squared plus 8x plus 15. Then, rearranging the equation, it will give us negative x squared minus negative 15 all over 8 equals x. If I transfer the positive x to the right of the equation, the resulting expression can be interpreted as the transformed equation in line with the fixed point method. So it means that this equation will be used to determine the value of one of the roots using the iterative process. For example, we choose our initial value as x equals 1. And once we substitute this value to the rearranged equation and do the iteration process, it will later bring us to the expected value of the roots. However, if we wish to find the other value of the root, we can't use this equation since it is dedicated for that particular root. Well, if you remember, one of the name of this method is one-point method. I guess now it makes sense. So we have to rearrange the equation in another form. Say for example, negative 8x minus 15 all over x is equals to the new value of x. Another major issue is the convergence of the solution. Under fixed point method, we can check the convergence of the solution using the absolute value of the first derivative of the function g of x. If the absolute value of the first derivative of the function g of x is less than 1, then the solution will converge, since the error will decrease each iteration. While if the absolute value of the first derivative of the function g sub x is greater than 1, then the solution will diverge, since the error will increase each iteration. To deeply understand the principle, let's solve a problem we used in the previous methods so we can compare the performance of both methods. Find the roots of the equation where f of x is equal to 0 with a stopping criterion of 0.001, where f of x is a function equals to 3x plus sine x minus e raised to x. To start the solution, let's set this area as the number of iteration and the value of the initial guess. But before we proceed, let's first rearrange the equation. So e raised to x is equivalent to 3x plus sine of x. And then we will apply ln to remove the exponential. So x is equivalent to ln of 3x plus sine x. The right side of the equation represents g sub x. So to determine the defined value of x, we will use ln of 3x plus sine x. And to assure the convergence, we will determine the first derivative of g sub x. So g prime of x is equivalent to 3 plus cosine of x all over 3x plus sine x. So, let's start the solution by having an initial value of 0.5. And since this is our input, it is not counted as an iteration. So let's first check if the solution will converge by checking the first derivative. So g prime of x or g prime of 0.5 is equals to absolute value of 3 plus cosine of 0.5 all over 3 multiplied by 0.5 plus sine of 0.5. And that is equals to 1.959. Since the result is greater than 1, the solution will diverge. So we have to change the initial guess, let's say 1.0. So g prime of 1.0 is equivalent to the absolute value of 3 plus cosine of 1 all over 3 multiplied by 1 plus sine of 1. So absolute value, and that is equals to 0.922. Since the result is less than 1, the solution will converge, and we can now determine the defined value of x. So x is equals to g of 1 equals to ln of 3x or ln of 3 multiplied by 1 plus sine of 1. And that is equals to 1.346. This time, we will check the relative error of the present and previous value of x. So epsilon sub n is equivalent to the absolute value of 1.346 minus 1 all over 1.346. And that is equals to 0.257. Still far from the stopping criterion, so we will proceed the solution. For the first iteration, the defined value of x will become 1.346. Again, let's first check if the solution will converge by checking the derivative. So g prime of 1.346 is equivalent to the absolute value of 3 plus cosine of 1.346 all over 3 multiplied by 1.346 plus sine of 1.346. And that is equals to 0.643. Since the result is less than 1, the solution will converge, and we can now determine the defined value of x. So x is equivalent to g of 1.346 is equivalent to ln of 3 multiplied by 1.346 plus sine of 1.346. And that is equals to 1.612. Epsilon sub n is equivalent to the absolute value of 1.612 minus 1.346 all over 1.612. And that is equals to 0.165. Still far from the stopping criterion, so we will proceed the solution. For the second iteration, the defined value of x will become 1.612. Again, let's first check if the solution will converge by checking the derivative. So g prime of 1.612 is equals to the absolute value of 3 plus cosine of 1.612 all over 3 multiplied by 1.612 plus sine of 1.612. And that is equals to 0.507. Since the result is less than 1, the solution will converge. And now, we can determine the defined value of x. So x is equals to g of 1.612 is equals to ln of 3 multiplied by 1.612 plus sine of 1.612. And that is equals to 1.764. So, for the relative error, epsilon sub n is equals to the absolute value of 1.764 minus 1.612 all over 1.764. And that is equals to 0.086. Quite near from the stopping criterion, but still we will proceed the solution. For the third iteration, the defined value of x will become 1.764. Well again, I suppose that you now understand how to determine the roots of an equation using fixed point method. Let me now show you my MS Excel computation that presents the convergence of the solution. As you see, it took 9 iterations to satisfy the stopping criterion, and as you also notice, the value of the root is equals to 1.89. And as I mentioned earlier, it will require another arrangement of the equation in order for the method to determine the other value of the root. In my opinion, this method has a lot of disadvantages as compared to the other methods. So that concludes the discussion of manual computation using fixed point method. Again, this last part of the video is for the computerized computation using fixed point method. So allow me to introduce some new features of VBA to enhance our coding. So insert another module for our new method and rename it as fixed point method. Then create a sub-procedure and name it fixedPoint. This time, I will first define the variables with their variable types like double and integer. We will also use input box, so instead of declaring the value of the variable inside the code, we can now use dialog box to ask for the input. This line is the content of the dialog box, while this one is the title, and this right here is the initial content. For the iterative process, we will use the do until loop with almost the same content with the previous codes, with the determination of the find value using g sub x, and the checking of convergence using the first derivative of g sub x. Take note that for both of this g function, we will use function procedures. Another point is since ln function is not supported by VBA, we will use worksheet function. In a way, we are calling the formula inside the MS Excel itself. I also want to highlight that we will use a message box under the convergence line so that the code can communicate to the user. This line is the content of the message box, while this one is the title, and this one right here is the message icon. While this line over here is used to skip the line in between, since initially, the relative error is empty, since without doing this function, the code will force to end. And lastly, the cell function that transfers the value of the variable inside the VBA to the MS Excel. So don't forget to change the coordinates to avoid erasing the output of the other methods. So if I run the code by pressing F5, it will ask me about the initial guess, as well as the stopping criterion. And then, the solution will proceed. So, the code has an output of 9 iterations to extract the root with a value of 1.899 with a relative error of 0.00047. Again, you have to change the content of the function procedure to determine the other value of the roots. It means rearranging the equation. So that's it for this video. Hopefully you learned something new. So thank you for watching and see you soon. Keep safe, guys.